In this video, we are going to look at the debug round of the World Computing Championships. So on the Eunoia Ventures website, go to the World Computing Championships tab and click on Sample Problems. And this will get us to this home page where we can press Debug. And then we can press Start Round 1, and then it will give us 3 sample questions. So let's work through the first question called multiplication. So here we're given a statement. The following code takes 3 integers as an input, a, b, and m, and outputs the product of a and b mod m. More formally, it aims to output a times b mod m. And what this essentially means is that when you multiply a and b, a times b divided by m, it outputs the remainder of that, as that is what mod is. So the input format and output format they've given us is 3 non-negative integers a, b, and m. So they can only be 0 at a minimum. And an output format, a single integer, the result of the mod division of a multiplied by b. So once again, that is a times b divided by m, and that the remainder that comes from that. So we were given some constraints for the input. So a, b, and m at a minimum can be 0, and at a maximum can be 10,000. And then we're given a pseudocode. So this pseudocode aims to output a times b mod m for any input a, b, and m. But there is a problem in the pseudocode that the participant needs to find, which for some cases will output a wrong answer. It won't output this exact expression, a times b mod m. It will output a wrong number. And they've given us a pair of input and outputs, 2 sample inputs and outputs, where the output is still correct. So here the output will be 0 for this sample input 1 in both the pseudocode and the intended output. And here it will be 1 for both the pseudocode and the intended output. And we can test that. If we look at 3 and 4, 3 times 4 as per a times b mod m, 3 times 4 is 12, and divided by 2 has a remainder of 0. And the sample output, from the pseudocode is 0. So it is output the correct number. As for 3, 5, and 2, 3 times 5 is 15. When you divide that by 2, you'll get a remainder of 1. So this 1 is correct. So the pseudocode works for these 2 cases. Now let's analyze the pseudocode to see what can possibly be the issue. So here we have procedure mod multiply a, b, and m, and then it returns an integer. So here you can interpret that this is where you're inputting a, b, and m, and this integer means that they're in integer format. And while this name may not be exactly like Python or C++ or whatever programming language you're familiar with, this code has, of course, some similar syntax and similar functions that you can draw some similarities to with your preferred type of code. So you can still interpret this code. It's not completely a new language. So, and then it returns a mod m. So you can obviously interpret that as just a mod m times b mod m. And this is not exactly the same. You can see this is not exactly the same as a times b mod m. There's a difference in the expressions there, and that is likely where the problem in the code lies. And then it will output this expression. So if we test these inputs in this expression, we'll see that it still gets the same answer, but let's test them anyway. So a mod m, so here this is a, this is b, this is m. 3 mod 2 is 1, and you're multiplying that by 4 mod 2, which is 0. So 1 times 0 is 0. So it gets us 0 in a different method, but it's still the same answer. As for 3, 5, and 2, you're doing 3 divided by 2 with a remainder of 1 times 5 divided by 2, which is a remainder of 1 as well. So that's 1 times 1, which is 1. So once again, that is a different method from just doing 3 times 5 mod 2, but it yields the same answer. So what we need to do is we need to find a specific input case that for this expression inputs a wrong answer. It does not input the same number as you would get if you did this. And to solve this problem, to figure out what possible input case this could be, we have to think about the properties of the function of mod itself. So mod is a remainder function, and a property of a remainder is that it can never be equal to or greater than the divisor. If you have, say for example, a divisor 4, and you're doing like 9 divided by 4, that will have a remainder of 1. If you're doing 10 divided by 4, that will be a remainder of 2. 11 divided by 4, remainder of 3. If you go to 12 divided by 4, which divides perfectly, it will be a remainder of 0. But never can that remainder reach 4 or greater than 4. So the remainder will always be less than the divisor. And since this is one whole mod expression, this is just a times b mod m, this will never yield a number equal to or greater than m. This result, this output, will always be less than m. But since this expression is the multiplication of this mod expression and this mod expression, it may not necessarily be greater than equal to, it may not necessarily be always smaller than m. This could still possibly be, this times this could still possibly be greater than equal to m. A mod m, that will always be smaller than m. B mod m, that will always be smaller than m. But the multiplication of these two remainders may not necessarily always be smaller than m. So if we take that case of 4, if m is 4, this remainder, the output, can only be 0, 1, 2, or 3. But this multiplication, to get output that would be different from the output, the intended output, we need to get a multiplication of this that is greater than 3, that is equal to or greater than the divisor. So for example, we could get 4. So 4 is we need to find two numbers. If we can make this times this 4, we could say that this is equal to 2 and this is equal to 2. So that this and this would multiply with 4, and hence it would return 4, which would not be possible from this expression. So if a mod 4 is 2 and b mod 4 is also 2, this would return 4. So we could, since we're set on m equals 4, we just need to come up with two numbers a and b that would follow that expression, 2 mod 4 times 2 mod 4. So something mod 4, the first number mod 4 is 2. So 2 mod 4, if a is 2, 2 mod 4 is 2, because 2 divided by 4 is simply a remainder of 2. Now let's go to b mod m. You could also do 2 divided by 4, you could possibly do 6 divided by 4, but 6 divided by 4 is also a remainder of 2. It's 1 with a remainder of 2. So if a is 2 and b is 6, you would get 2 times 2, which is 4. But if a is 2 and b is 6 here, you get 12, which divided by 4 will have a remainder of 0. So this, the intended output would be 0, yet the actual output, the wrong output, would be 4. So if a is 2 and b is 6 and m is 4, that is one possible input case that would output a wrong number. And that's basically what you need to do. You need to find the problem in the code, and then you need to find the input that would exploit that problem. And so once you input the numbers, you will either get correct or incorrect. If it's correct, you have successfully found an input case that would output a different number or a different output from the pseudocode than the intended output. But if it's incorrect, it would still output the same from the pseudocode as the output. So if it's incorrect, you haven't quite found the problem in the pseudocode yet. So if we input 2, 6, and 4, which we've already mathematically deduced, will have a different output from the pseudocode as the output, we will get correct. So here we can clearly see that from here, from the pseudocode, we would output 4, but the actual output from this test case is 0. So this is essentially how to go about solving the questions in the debug round. Find the inconsistencies in the pseudocode and then input a specific test case that would yield a different number or output from the pseudocode compared to the actual intended output.